Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing. So we only have couple of topics left in the numerical methods for using MPI. So I hope to kind of wrap it up today for this chapter. So the couple of things remaining are the solution of system of linear equations, and then basically solution of partial differential equations, which we saw in the MPI in the OpenMP discussions that it could be either parabolic or elliptic, right, type of partial differential equations. And elliptic partial differential equations essentially are kind of a boundary value problems, right, where if you have an example would be Poisson's equation, and which when discretized would basically result in a again in a system of linear equations, right. And then the parabolic type, depending on the time stepping we choose, we either get explicit or implicit methods, that is in time, right, and we can accordingly deal with these either using, if it is an explicit scheme, then by direct substitution. My throat is a little odd, so excuse me for that. If it is implicit, again we end up with a system of linear equations. Okay, so essentially today's discussion about all these things boils down to how do we solve a system of linear equations, right. Some of this material we have already covered in the context of OpenMP, in the numerical methods for OpenMP. Okay, so when it comes to the solution of system of linear equations, or AX equals B, where A is a matrix, X is the unknown vector, and B is the right hand side vector that is known, right, and the coefficient matrix is also known, and we have to calculate what is X. We could kind of categorize the methods into direct methods or iterative methods. So the direct methods, an example is basically your Gaussian elimination, or in other words, it is basically your LU decomposition. And the examples of iterative methods are Jacobi iterative method, then we have the Gauss Seidal method, as well as we also have the Gauss Seidal successive over relaxation method, right, that is basically your GSSOR. Okay. Excuse me. All right, so what we say here is that of course we have looked at some kind of an LU decomposition, but what we looked at before in the context of recursive doubling or cyclic reduction was that is for basically for a tridiagonal system. Now we are talking about here a dense matrix, and it doesn't really have a banded structure. Okay, so let us begin our discussion in today with the Gaussian elimination, and thereafter we move to Jacobi and Gauss Seidal, and this can be automatically applied once we know how to calculate Gauss Seidal, because Gauss Seidal SOR only differs from Gauss Seidal with the over relaxation factor, that is omega, right. So this can be easily implemented, so there is nothing new that we need to discuss in this context. Okay, so let us start with Gaussian elimination. Okay, so we are talking about basically dense matrices, right, dense matrices, and then these matrices actually do not possess, let's say, a banded structure. I think by the way of saying it's a dense matrix, do not possess a banded structure. So essentially what we are saying is that the matrix is dense, and then there is no banded structure. That means this is not like a tridiagonal or a pentadiagonal system, right. So essentially we have to see if we can calculate the solution vector X for such matrices, for such linear systems, that is Ax equal to B, right. And then of course we know that a variation of Gaussian elimination is your LU decomposition, and this is now the full LU decomposition, right, unlike the tridiagonal system of LU decomposition we have seen in the context of triangularization of the matrices. Okay, so essentially in Gaussian elimination there are two steps. The first step is your forward elimination, and the second step is your backward substitution, right? Now before we begin, kind of a quick note here. It is not very often, it's kind of very rare that we have to work with matrices directly. So matrices directly is very rare, and most of the times you would not be, unless only except for the small size matrices, you would not be have to solve for this system using using the entire matrix. Okay, so as a result, because the number of operations required and everything is so complex, so large when it comes to direct methods, so direct methods are not often used. And also the matrices that you get would not be dense like the ones we are talking about here, using, let's say, if you have a CFD or if you are working with CFD or any other field. But in certain contexts the matrices can be dense. There are a few exceptions. Those are, for example, if you have to calculate some kind of a transform of a signal or something in electrical engineering or even in fluid mechanics. If you have to calculate transforms, let's say something like Fourier transforms, you may have to work with certain transforms require working with the full matrices, and also some things in computational chemistry might also would call for working with full matrices. Otherwise there are not many instances, unfortunately, that that you have to work with full matrices, or fortunately. Okay, so that means we have two steps in Gaussian elimination, which are basically the forward elimination and the backward substitution. So what does the forward elimination do? Forward elimination, what it does is it will basically take Ax equal to B, and it's going to convert in the using elimination steps. It's going to convert this matrix system into Ux equals G. Okay, let's say where U is the upper triangular matrix, and then G is the new right hand side vector. Okay. So that's what it is. And then once you have an upper triangular matrix, you could actually use backward substitution and calculate the solution vector X. Okay, all right, so that is the idea. So if I were to write down this matrix A using equations, so then what we have is we have basically A11 x1, A12 x2, and all the way to A1n xn, and then the second equation will be A21 x1, A22 x2, all the way to A2n xn. And then if we take some ith equation, that will be AI1 x1 plus AI2 x2 plus all the way to AIn xn, and then the nth equation would read AN1 x1 plus AN2 x2 plus all the way to ANn xn. Excuse me. Right, so that means our A matrix that we're talking about has coefficients A11, A12 all the way to AN, and then AN1, AN2, and all the way to AN. Okay, so that is the system that we're working with here. Okay, let me just pause for a moment. Okay, so the idea here is that now we have to define multipliers, right? Once you identify a particular row, let's say the idea here is that you identify the first row, and then the first element would be identified as the pivot element, right? And then the first row is the pivot row. Then using the pivot element, we would like to make all the elements that are below the pivot element as zeros. Okay, so we would basically define we basically do row operations such that all the elements below this would become 0, and then every other element below the first row would basically get modified, right? And then while we do so, we also have to work on the B matrix as well, which I have not shown here. So this is your B vector, so that also gets modified. Of course, the first element doesn't get modified because that will remain, whereas the other elements get modified. Okay, that means in the so we have several steps here. So the number of steps go from essentially from, if you call this as 0 or 1, it basically goes from 1 to n minus 1, right? So you go from n minus 1 steps, and then in those steps you would convert this A matrix into an upper triangular matrix. Okay, so we define the multipliers, and the multipliers are different for each of the rows. right? And each of them, once you identify the pivot row, if I call the multiplier as MIK, okay, then this is basically your AIK at the kth step divided by AKK at the kth step. Okay, so it means your I goes from k plus 1 all the way to n. Okay, so in the first step you have the first row as the pivot row, and then you make everything, all the elements below the pivot element will be made to 0, and all other elements will get changed. And then in the second step, when k equals 1, you basically you identify this as the pivot row, and then you make all these elements as zeros, and then all of these will get modified and so on, right? That is how it kind of proceeds. Okay, so then we have now defined the multipliers. Now using these multipliers, we have to kind of calculate the new values for the coefficients in the matrix as well as on the right hand side vector. So that would be Aij in the new values in the step k plus 1 would be Aij k minus, use the multiplier that we have just calculated, that is Mik times Akj at the previous level that we have. Okay, similarly Bi, the right hand side vector also gets modified. This would be Bik minus Mik times Bk at k, okay, in which you are basically I and j go from k all the way to n, right? Okay, so what we see here is that we would need access to so all the rows would require access to the pivot element, that is akk of k, and also all the rows, that is I going from k to n, that is all the rows below the from the pivot row also would require access to akj. This is basically, it would require access to the entire row here, right? Because if k happens to the row, so this basically requires entire row values, right, also to modify all the elements below the pivot row. Okay, now so that means, and then we can keep doing these steps for k equals 1 2 all the way to n and n minus 1, and then you essentially get this system that is which basically gets modified into a n of x n times to the b n, right? So basically this basically is your final matrix, that is your nothing but same as your ux equals g, right? If I were to denote a to the n as u and then b superscript n as g, okay, then of course you could calculate the unknown vectors, that is basically xk, using backward substitution. Okay, that means a k k, and then you basically have bk of so in any step bk of n minus sigma j goes from k plus 1 to n akj xj of n, right? So basically you could calculate while k is going from n minus 1, n minus 2, and so on all the way to 0, right? Okay, so that is basically your so then you could calculate what is xn minus 1, and so on all the way to x1. So that is the backward substitution phase. All right, so excuse me, so what we basically see here is that the backward substitution base is kind of inherently serial, right? So even if you use a distributed memory system, your xk, unless you calculate xn, you cannot calculate xn minus 1, and only if you calculate xn minus 1 you could calculate xn minus 2, and so on. So this is inherently serial. As a result, even on a distributed memory system, we cannot parallelize this one, or neither on a shared memory system as well. So we cannot parallelize this. This is inherently serial. However, the elimination phase can be made into parallel, right? This can be parallelized. And we also note that the maximum complexity in the computations comes from the elimination phase, whereas the backward substitution is only order n, so it doesn't really make a lot of sense to, even if we don't do it, even if we are unable to parallelize it. Okay, all right. So and we also see that because we are kind of not so once a particular row is once the pivot row is moved to the lower lows here or the upper lows here. So if you have k1, k2, and so on, then the elements in the previous rows are basically untouched, right? So that means that means if k equals n minus 1, that means we are doing the last step, then only the elements in the nth row get modified. That means everything above it will not be modified. So that means this basically tells us that if you look at matrices AK and AK minus 1, both these matrices, so this is basically the same A matrix, I am denoting with a superscript. This basically denotes that the state of the matrix at step k, okay, and then this is at step k minus 1. Okay, so what this basically tells us is because only the elements below that are below that particular iteration or step are modified, that means AK and AK minus 1 at any k will have the first k minus 1 rows will be identical, right? Will be identical. Of course, here I am basically talking about two different A's, but in the implementation you just have a single matrix A. You do not keep copies of different steps unless you want to have a copy of A in which you have to basically back it up before you do the before you call the Gaussian elimination, okay? Because once you enter the Gaussian elimination, A gets modified into U, okay? So you may actually lose it. So as a result, if you want to have the original matrix, you have to first take a copy before you come to Gauss Seidal. Okay, so what this basically tells us is that because the elements in the rows one below it are only modified, the rows above it are actually remain the same, okay? So that basically tells us that as we proceed with our algorithm, as k increases, right, as k keeps on increasing, as we go to a higher and higher case, then what happens is that there are rows which have which require no modifications, right? Essentially the rows which require no modifications also increases, right? That means if we have some processor P is assigned to this particular row, then that processor will basically become idle, right? So for example, let us say we draw a matrix and then we have, let's say, several rows in here and then we have rows 1, 2, 3, 4, 5, 6, 7 and so on, okay? So let's say if you have essentially grouped, let's say, 2 of these rows together and assigned it to different processors, right? And processor, let's say we have 4 processors, so you have either I can call it P1, P2, P3, P4 or P0, P1, P2, P3, right? So you have n prox equals 4. Then once you cross k equals 1, k equals 2, so when k equals 3, then processor P0 has essentially no work to do, right? Because it has already finished its job, so it has no work to do. So as a result, this will be idle. Now after again, once k reaches 5, then these 2 rows also are untouched. As a result, P1 also will be idle, okay? So it turns out when it comes to distributing the memory, for Gaussian elimination, then a row-wise block structured allocation, right, as we have done above, is not good, is not a great idea. Why? Because essentially as some of the processes or more and more processes would become idle as k increases, okay? So in order to have better load balance, instead of having a row-wise block structured allocation, we go for row cyclic distribution of the matrix A and the right hand side vector B, okay? So this would basically allow us to have okay, so we go for row cyclic distribution of the matrix and the right hand side vector B, because this would result in a better load balancing of the matrix. Okay, so essentially what we're talking about is, when you say row cyclic, we don't assign it in this way. Rather, what we do is that let's say, for example, I have only 3 processes, that is 0, 1, 2, and then these are the rows. I have several rows, and I would assign, let's say, one row. Let's say for the example, I would assign one row to one process, then this will be P0, P1, P2. Then if I have only 3 processes, then again I would give the 4th row to P0, right, and then P1, P2, and then P0, P1, P2. That way your P0 would get, let's say, the first, the P0 would get basically the first row, as well as the 4th row, right, as well as the 7th row, and so on. So as a result, and then your process 1 would basically get this one, this one, this one. So as a result, as k increases, you know, your number of processes would not become idle, because the process 0, even if you are at this location, still has some rows left with it, and then it has to do some operations. Okay, so this turns out to be, so as a result, a row cycling implementation turns out to be, distribution turns out to be better when it comes to Gaussian elimination, rather than a row block-wise implementation, okay, or distribution. Fine. So far so good. Then let us see if we can basically write a kind of a pseudocode for this Gaussian elimination, which you can implement later on. So let us look at some kind of a pseudocode or algorithm for parallel Gaussian elimination. Using row cyclic distribution. Okay, there's no dot here. Okay, that's fine. Okay, fine. All right. So let's say if we have a function, we call it, let's say, Gaussian elimination. Okay, and then this function basically may take in the matrix as well as the right hand side vector. Then we basically have declaration of variables. Okay, and we have this matrix A as well as the right hand side vector B, which is n by n and n by 1. And of course we also have to allocate what is the solution vector. So solution vector, let us allocate as x of n. Okay, now the thing here is that the k that we are talking about, so if we denote k as the pivot row, now the pivot row will keep changing depending on the value of k, and then the pivot row may belong to one of the processes, right? So as a result, but then the entire pivot row is required, as we have seen in here AKJ. So entire pivot row is required in order to do the elimination, and also of course the pivot element is also required when you calculate the multipliers. So this is required by all the rows that are on which it will be operated, that is k to n. As a result, we need to so whoever has the pivot row has to broadcast that, or has to send that to all other processes. Only then we can calculate the multipliers, respective multipliers for those rows on all other processes, and then the entire pivot row needs to be sent. So that is the only catch here. So what we do is that so basically we have to have some buffer that we allocate. Let us call it a row that basically represents our pivot row. Okay, and then pivot row could be assigned as n, but what I would like to do is we would have instead n plus 1, because together with by eliminating A, we also have to do operations on the right hand sector vector B. So the element of B, that is basically your bk also needs to be passed to all the process. Okay, so as a result we would have the pivot row together with the right hand side vector b, which would be passed in one go using this row n plus 1. So that means this will basically hold 0 to n minus 1 will be using the values of a, k, j. Values will be stored here, and then the last element n will basically be p, bk. Okay, so those values will be that is basically the right hand side. Okay, then we have the forward elimination step. Excuse me. So basically we have a for loop for k goes to k equal to 0, k less than let's say if you have a matrix going from 0 to n minus 1, then it goes to n minus 2, and then k plus plus, right? So if it is Fortran, you have to have slightly different. And then first we need to see basically who has the pivot row. So that means if your k, because now k is your number, that is basically your row numbers, right? So that's basically if you have 0, 1, 2, 3, 4, 5, 6, 7 and 8 and so on. So we need to see if that particular row, right, 2 belongs to P2 or P1 or P0. So for that what we need to divide this by the number of processes that we have, which this in this case happens to be 3, right? And then see if the remainder happens to be 0, 1, 2 and so on. Okay, and then we would say if that belongs to a particular process. So for that I would do is k, calculate the remainder using n processes, and if this happens to be same as your process ID, then you basically, then that particular process has the check for process that has the pivot row, right? So then what we need to do is we need to basically copy the pivot row elements so that it can be basically sent to all other process, right? This is not good. Copy the pivot row values. That means we go for I can either go for j equals 0 or j equals k, and then j less than n, j plus plus, because we don't need the values before that anyway, because they will be already made into 0. Then what we need is we need to copy this into our row, that is our pivot row of j equals a of kj. So copy all the values for that particular row, and then also you need to copy the row of n to be the b of k, right? And then we are basically done. So that is basically done with the copying. Then we need to broadcast to all the processes this pivot row. So basically broadcast pivot row element values to all processes, right? So what we do, we basically call our MPI broadcast function, and then we basically send, either we can send buffer or the row that we have, row plus k. We could send only whatever is required, that is basically the part of this thing, or we could even send the full one. So if we send the part of it, that's basically row plus k, we send that. This is basically the base address, right? And then the elements we send are n minus k plus 1. Otherwise we could send the entire row, and we can send n values here, right? Or n plus 1 values. Okay, so both of them are valid, and then depending on whether we are sending a double or a float values, we could have MPI double. And then who senses this, basically sent by k upon n procs process, right? And then we have MPI communicate world. Okay, that's all. So that's basically sends the pivot row to all the process. Then we have all the elements that we need on every process. Then basically we go about with our row operations. So how do we do with the row operations? Now here I would be using a global index I for assigning or referencing the matrix A, which may not be the case in the C, because you may not be able to allocate the values of A rows with the global indices. Okay, so because C would always allocate them from if you, let's say for example, process 0 has the 0th row, 4th row and so on, or 3rd row and the 7th row and so on, or 4th row, then you basically in C you would only allocate from 0, 1, 2. Okay, whereas in Fortran you can allocate from for example, let's say 3 to 6 and so on. You can still reference with the global index I. So herein I am using the global index, but you probably have to have another reference data structure which would give you conversion from global index to local index. So if for I equals k plus 1, what I would do is I have to basically, depending on the row we are in, on every process we have to go to that particular row. So if I percent n prox is not equal to my ID, then you basically do a I plus plus, right? So once you exit this, you get the I value that you can use in the for loop below for doing the row operation. So basically for I less than n, I plus equals, we need to now skip by n prox, right? Because if you go back, the operations would be done by on this one by 0 will do operation here, then it will do an operation again on this one and then on this one. So we have to skip by n prox in the global referencing. Otherwise you have to recast this into local values, either using another buffer array or a location array, which would basically map your global to local. Okay, so we skip that. Then these are the row operations. So row operations are L of I equals A of ik divided by the row that we have received, row of k, right? And then we have our k is actually now j equals k plus 1, j less than n, j plus plus. This is basically your columns and these are your rows, right? And this is your pivot element. Okay, now for j equals k plus 1, j less than n, j plus plus, what do we have? We have to basically do A of ij equals A of ij minus L of I times row of j. Okay, so once we are done with that, then we have to also do the row operation for the B matrix. So for the right hand side vector, so B of I equals B of I minus L of I times row of n, right? Because row of n contains the B value for the pivot row. Okay, so once we are done with this, then forward elimination is done on every process. Okay, of course you need to pay attention to the indices because I have used kind of global indices, which may not be possible to do in C, but it's possible in Fortran. Okay, then we have the backward substitution. So let us do the backward substitution. Okay, so what we have to do, we basically have another for loop. So that is your for k equals, you begin with the last value, k equals n minus 1, k greater than or equal to 0, k minus minus, you reduce, right? You basically do a backward operation. Then again, if your k divided by n prox happens to be your ID, right, your processor ID, then what you need to do is you need to first calculate the initialize sum equal to 0. Essentially we have to do the backward substitution, so which basically can be done again using a summation. So for then we have another for loop for all the columns, j equals k plus 1, j less than n, j plus plus. Then we have sum equals sum plus a of kj times x of j, right? This is the unknown we have to calculate. Then once you calculate all these some values, right, then you basically have to calculate what is your xk, right? So your xk calculation is this can be done outside, right, outside this. So we remove this. So we have the summation, then your xk would be equal to 1 by akk, or right, to multiplied by b of k minus sum, right? We do that. Okay, that's done. Then once you have the values of x of k, we need to now broadcast this to all of the process. So we kind of come out of this loop because k and this will be only executed one of the process. So we come out of that, and then we broadcast the x values because those are required for the next process, whichever is going to do the next n minus 1 next k value, right? The k n minus value. So we broadcast x of k, which is basically one value of MPI double, and then who has to send this? K percent n prox, processor has to send this, and then the communicator is MPI communicate world. Okay, fine. So that's what we have. That's the end of backward substitution and end of the function Gauss Seidal. Okay, so that's how we can kind of implement our Gaussian elimination using forward elimination, Gaussian elimination using forward elimination and backward substitution. Okay, so we have used a row cyclic implementation. Now you may wonder, can't I use a blockwise, row-wise block structured implementation? You could do that. It's going to be not very efficient. And as we have also learned, checkerboard distribution, you could also do a checkerboard distribution like what we have done in the matrix multiplication. We could do the checkerboard distribution for Gaussian elimination, which I'm not going to talk about it today. We will not learn this, but if you want, you can even extend this to checkerboard distribution. Okay, fine. So that kind of finishes the parallelization of Gaussian elimination. Then let's go back and see what we have. Okay, we have to now look at the iterative methods. That is basically your Jacobi method and Gauss Seidal, which could be coming from the solution of an elliptic partial differential equation. Okay, so we discussed in the context of numerical methods for OpenMP, if you have an elliptic partial differential equation, then what we basically have is we have del square phi equals f, right? This an example is basically a Poisson's equation, right? So this would basically result in a in an algebraic right? So on a 2D rectangular domain, if you use finite difference method, we could write this as del square phi equals f as dou square phi by dou x square plus dou square phi by dou y square equals f of ij, right? And if we differentiate this, you have phi I plus 1j minus 2 phi ij plus phi I minus 1j divided by delta x square plus phi I j plus 1 minus 2 phi ij plus phi I j minus 1 divided by delta y square equals fi comma j. Okay, so that's what we have. So we are talking about a rectangular domain with basically grid sizes as delta x and delta y. Okay. Now what, depending on so now we basically have to solve for this either using either a Jacobi method or a Gauss Seidal method. Then if we choose the Jacobi iterative method, then what we have is we could write phi ij k plus 1 as phi I plus 1j plus phi I minus 1j plus phi I j plus 1 plus phi j minus 1, right? And we have minus del square f of ij and all of these divided by 4. Okay, and then now depending on what values of phi that this phi ijk plus 1 depends, we either have a Jacobi method or a Gauss Seidal method. And in Jacobi we have all of them are at the previous iteration level, so these are all at the previous iteration, right? As a result, what we noted is that the Jacobi iteration, because phi ij k plus 1 are all independent equations, this could be performed, so these could be computed in parallel, right? Yeah, okay. So that basically there is a lot of scope for parallelization when you use Jacobi method. And again, we could look at we are basically looking at a 2D domain. So we can now look at again two different decompositions. One is a one-dimensional decomposition or a two-dimensional decomposition. And if you are looking at a one-dimensional decomposition, then what we basically are talking about is, so we have this grid, right? I think probably better off drawing this better here. So we have a 1D grid here. Okay, so I draw some representative elements. Okay, and then I grid points here, and then we have so this is the representative grid or mesh here. Then we have to kind of decompose it either using one dimension or two dimensions. Let's say if we start with one dimension, then what we do is, let's say we assign the first two to one process, and then the next two to another process, and so on. Okay, so basically here the first two are assigned to one process. This is to P0, this is to P1, this is to P2, and so on. Okay, if we do it this way, then when you try to write this particular equation, when you try to calculate this for let's say these grid points, right, for these grid points, then they would basically, because they have this value of phi I j minus 1 that is basically required here, so they would need a value of this one, right? So these values that are shown in blue are required to compute this value shown in red, right? And similarly, when you try to calculate, let's say we want to calculate the value shown in red here for process P2, then the values shown in blue here are required because it depends on phi I j plus 1. Okay, now we may say that, okay, now what about creating virtual points or ghost points? Yes, that is what exactly we should do. And initially when we begin, we probably can fill up these values with whatever we have, but however, because we are using an iterative method, we need to exchange data after every iteration, right, between the processes. Okay, so that means what we need to do is, if I redraw this figure for each of the process, let's say if I draw it for P1 or P0 and P1, then P0 has 2 1 and 2, and then it has also, so basically it has all these points, right, all these points, and then it will also have some virtual points that it will create, right? And similarly, so this is for basically your P0, and then if I draw P1, so P1 would basically have 1, 2 points here. I hope that they are all matching here, and then it also has to have some points here which are ghost points for P2, right? Okay, then how do we need to exchange the data? After every iteration, right? Let me draw a few more here, okay, because 2 is too small. Okay, let's say we have this much. Then after every iteration, these ghost values needs to be updated by process P1, and similarly these ghost values, all of them needs to be updated by P0. Okay, so that is how it works. So essentially fill all these values from these values, and then update all these values from these values. Okay, so that is how we would need data exchange after every iteration. So that the ghost, the ghost values are updated. Okay, they contain the right values. Okay, now instead of a 1D decomposition like this, we could also go for a two-dimensional decomposition, and that's going to be little more tough in terms of, or little more complicated in terms of the messages that we receive. So instead of having process aligned like this, we could also have processes split like this, right? For example, let's say we may have a process like this and process like this, so that now one process will have it, all this will be on one process, and another process would have this data, and another process would have this data, and so on. Okay, so that means we could also use a 2D decomposition. Right. Okay. So, and if we have a 2D decomposition, I'm kind of drawing here how the mesh kind of looks like after the decomposition. Okay. So I kind of separated. So let's say we have 1, 2, 3, 4, 1, 2, 3, 4. So these are all together. I just made it to separate process here. Okay, so these are all, whatever I have drawn here, all the are basically all the grid points here belong to the respective processes. Okay, so that kind of belong to respective process. So that means let's say this is process 0, this is process 1, this is process 2, and this is process 3. They also need to, of course, have ghost points, and then the ghost points are drawn here now. So these are the ghost points in the column, these are the ghost points here, and these are the ghost points here, and here, and for the other process here, and so on here. And then these are the ghost points here as such. Okay, so then we need to kind of update these ghost points with the exact or with the correct value. So this process P2 has to update them here after every iteration, and then P0 has to update these values here. Okay, similarly this column needs to be updated by P1, and then this column needs to be updated by P0. Okay, similarly this has to update here, and this has to update here, and so on. So there are a lot more messages need to be exchanged. However, the messages are now smaller, right? So that means after every iteration it has to exchange information between its neighboring process, depending on if it is an interior process or a boundary process. So if I were to so when you try to do this kind of exchange, you have to probably use this vector and contiguous data types we discussed in the context of derived data types. Okay, so you would probably require that. Okay. So that means if I were to put this together, basically we have the main iteration loop. So you have iteration equals 1 as your iterations are less than number of iterations, iteration plus plus, right? And then we have to loop over all the grid points that belong to a particular process. So every process does the following. What do we have to do? We basically have to look at for j equals 1 or 0, and then j less than j max, whatever is the max value for j, and then for I equals 1, I less than I max, I plus plus, right? So we have these two. Then we have to update what is phi of ij equals 0.25 times phi of I plus 1j plus phi of I minus 1j plus phi of I j plus 1 plus phi of I j minus 1 minus you have delta square times f of ij is what you need to do. Then once you are done with these two loops, then for every iteration, of course, you need to calculate whatever is the residual or error or tolerance, whatever, right? You have to calculate the error or residual. You can do that. Then you have to exchange data, right? Basically update ghost point values using using data from other processes. Okay, so that is the main step here. Now this exchange is what you need to do every iteration, because we are going with the Jacobi method. Okay, all right, so that kind of finishes the implementation of Jacobi method in 1D and 2 dimensions. Then let us take a quick look at the Gauss Seidal method. Okay, Now the Gauss Seidal iterative method. Okay, so the Gauss Seidal iterative method is kind of similar to the Jacobi method, but then we realize that when we are updating the phi values, there are some of the phi values are already updated, so why not make use of that? That is probably a good idea, but it is not a very good idea when it comes to parallelization, because you want to update phi ijk plus 1, you have phi I plus 1j plus phi I minus 1j plus phi ij plus 1 plus phi ij minus 1 minus del square fij divided by 4, right? Now what we realize is that phi I minus 1j and phi ij minus 1 are already computed. If we are talking about a serial implementation, then why not make use of the values in the current iteration for these and the values in the previous iteration for the other two. Now this is basically causes a dependency issue, for phi ijk plus 1, and basically makes it difficult to parallelize. And as such, we have seen two different methods in the context of OpenMP. One we saw is a kind of a diagonal solver, and then the other one we saw was basically a red-black coloring approach, right? So so in the diagonal solver, we kind of proceeded along the diagonals of the grid, of the two-dimensional grid we have, and the red-black coloring approach, we have kind of colored the grid points using alternate red and black colors. Okay. All right. So so let us see how we have done. The thing is, the diagonal solver is kind of good for the context of OpenMP, but making this implementation in a distributed memory system is not very effective in terms of scaling. So as a result, we will not be discussing the diagonal solver, although it can be done. We will only look at the red-black coloring approach in the context of Gauss Seidal iterative method for distributed memory calculations. Okay. So basically, we have now in red-black coloring approach, we have two passes or phases, right? So the pass 1 is basically where the red values are computed using the black values, right? And then the pass 2 is where the black values are calculated using the red values. Okay, so that's what we have. Okay, so if I were to draw a grid, so that's the grid. I think we have already seen this one, so it's not new. And then we have the, we denote some of the cells as red. So this is red, this is red, this is red, and then let's say this is red, this is red. Okay, so we have red like this. Then the remaining values are will be denoted as black values. So this is black cell, this is a black one. Okay, so that means we first calculate the red values from the black values. So the red values are calculated using the black values. So dependency is only on the blacks here, right? And then after that, the updated black red values have to be communicated to all other process. Then the black values will be updated from the red values. Okay, so we have these two steps. Okay, that means after phase 1, after pass 1, what happens is that the process Pij need to exchange data with its neighbors, right, and update red cell values. right, or red node values. That means it has to process Pij, has to exchange data with Pi plus or minus 1, J plus or minus 1, depending on whether you use a 1D or 2D decompositions. And then after pass 2 or phase 2, again Pij needs to exchange data of the black values that are computed between neighbors, right? Again, it has to exchange, Pij has to exchange with Pi plus 1 plus or minus 1 as well as J plus or minus 1. Okay. Fine. So now how does it look like? So I would like to just draw one communication here. So let's say we have 3 points here, and then we have 3 grid points. So I'm just drawing here. Okay, that means, let's say we have a red value here, a red value here, and then a red value here. Okay, and then we have black value. So we have a black here, black here, black here, and then this should be a red here. This should not be a black. Okay, so we have another black here, and then there is a red here, and there is a red here. Of course, we need to also come up with some ghost layers here, and then we have 2 ghost layers, one corresponding to the upper one, the other one corresponding to the lower one. And then when it comes down here, because this is red, we would basically have our red cell here, red cell here, red cell here, and here. Then the black cells are here, 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 and so on. Okay, then we need to of course exchange data after the pass 1, that is red values are updated. Then the red values needs to be updated everywhere. That means these have to be sent down, right? Of course, in this particular way, it doesn't look like there are red values that need to be sent here, but they need to be sent here because the ghost values here will be the red values, right? So only the red values need to be sent, so we don't have to send the the black here. So only the red values need to be sent by this guy to here and this guy to here. So essentially we basically have a one-way communication in which the red has to be updated here, right? And this doesn't require black values now, so it will be required only in the pass 2. Okay, so that we need to take care. And then coming to the ghost values for this one, this will be a black cell, this will be a black cell, and then this will be a red cell. So after pass 2, okay, but then this red value which is computed here needs to be updated here. Okay, so that needs to be sent here, so it is required. So it's a two-way communication. And then the black values needs to be sent to the process above after the step of updating the black values. Okay, so if I write a little bit of pseudo code or algorithm here, so then we have the main iteration loop, that is for iteration equals 1, iteration less than maximum number of iterations, iteration plus plus. Okay, then or you could have a while loop while your tolerance is greater than epsilon. You could have, then you have basically pass 1. Basically what we need is to do is solve for red cells, right? We need to solve for red cells. Then we need to exchange data or update red cell values into ghost points. Okay, and then we have pass 2, in which we basically solve for black values, and then we would exchange data to update black cell values into ghost points. Okay, or ghost points. Okay, so that's all is required. Of course, you need to do other calculations on convergence criteria and things like that. Okay, so that's pretty much it. So we kind of covered the system of linear equations, a solution of system of linear equation using both the direct methods as well as iterative methods. And with that, we pretty much finished the numerical methods in MPI part. So I'm going to stop here. Okay, thank you.